Supervised learning and nearest neighbor networks. So we're going to be looking at some applications here, both to regression and classification. So classifiers are algorithms that predict labels. First up, we're going to look at k-nearest neighbor classifiers. Suppose T is a test point for a given data set, and you've got some positives and some negatives, and you want to predict what T is. You choose a similarity kernel. Then you find the k-nearest neighbors of T. That's where the kernels are closest to 1. And then you have a classifier, a polling scheme or similar. So each neighbor votes their label, possibly with a weight W sub I for neighbor N sub I. Here we're using distance as similarity, and T has 3 neighbors. The vote's PPN, so the prediction is it's positive. In general, this is best for low noise linearly separable data, games, robotic arms, autonomous vehicles, extremely large number of sensor observations, for example, where you have one of finitely many possible responses. Vehicle, turn left, turn right, forward, backward. Game, take a card, stay with current hand. And to the extent that observations imply distinct responses, the label data tends to be separable. Let's look at an example. Look at a game called Catch a Falling Star. So the kNN classifier in general is great for simulations games. You need minimal randomness in the game, and you don't want the game to be so complex that the data set's intractably large. So catch a falling star. The stars fall vertically and you catch them. Or not. So at approximately 0.1 seconds apart, starting at 2 seconds after release, you observe the height and speed of the star and make a decision. Either grab or wait another 1/10 of a second. And you repeat until you make a grab attempt, and you only get 1 grab attempt per star. So a game is 100 stars in succession, each accelerated by gravity with a random initial velocity. Success is based on the time in which you grab. So here's success, here's failure. Initial velocities are samples, so stars reach that height at between 2 and 3 seconds, scores the number of stars grabbed. The data set, therefore, is 2-dimensional observations with labels, speed and height recorded for each grab decision, the label being the outcome of that decision, or that grab. True if successful, false otherwise. Now, a random strategy would be simply to uniformly randomly choose between grab or wait at each observation. So that means you would expect scores of around 10, because there are 10 intervals of 0.1 seconds between 2 and 3 seconds and 100 stars. So here's a simulation of 100 games with a random strategy. And we can visualize this by simply saying that if you're successful, color it green at that point SH and red if unsuccessful. So this is our decision surface for this game. So the nearest neighbor strategy for a given observation, use the label of its nearest neighbor to decide if to grab. After each game, you can learn the observations and the outcomes, but learning after each grab tends to be too slow. The next game then uses data from previous games, since you get this training data that's growing larger with each game. And the result is an algorithm that learns to play Catch a Falling Star. The first game, you use the random strategy to generate label data, and then after that, you continue repeatedly insert previous game outcomes into training data, and then use a nearest neighbor strategy. Here's a simulation of 100 games with nearest neighbor strategy. The data can be visualized, green if successful, red if unsuccessful. And here we have our decision surface. Notice there's not a whole lot of reds, but a whole lot of greens. So we can fix that by playing another 100 games to fill in our decision surface. And notice the data here is linearly separable. Once you realize the data is linearly separable, you really don't need any more training. There's no noise in this data. You just estimate the equation of the line and then you'll get perfect scores. Now, if the feature space is very high dimensional, for example, if instead of just grabbing, we are moving left and moving right, and suppose we had up to n stars in the display at any given time, so we can move left or right to try to catch a star, the feature space is now 2n dimensional. That means we're looking at the curse of dimensionality. Observations tend to be far apart. We'll need very deep KD trees, very time consuming. Huge sets of observations to learn to play this game. In other words, we need better classifiers. But let's look next at a regression problem. Regressors are algorithms that predict numbers. And you can just think of that as the labels being numerical rather than class. If t is a test point, then you have a similarity kernel. In this case, it's again a distance. You find the k nearest neighbors, in this case, case 3. And then a regressor means that you use some kind of a statistical measure, mean, median, something like that. You have each neighbor contributes their numerical label, and we're going to be using the mean here. And then the label of t is predicted, in this case, to be the mean of the labels of the neighbors. For example, let's look at what's called the small town zoo. Visitors to the zoo each rate a few of the exhibits from 1 to 5 as they leave the zoo for the day. So what is the data set? Well, 250 visitors rating of 150 exhibits. Exhibits are columns or features. And for illustration, we're going to use 0 if a exhibit is not rated by a visitor. So each observation is a row of mostly zeros. Now this is toy data intended only for pedagogy, but this is what the data looks like. 150 exhibits, 250 households or users. How long will visitors spend at a new exhibit? So suppose that the zoo measures the time spent or duration at its new wildebeest exhibit. So it needs to do crowd control, so it wants to be able to predict the duration of all returning visitors. It uses nearest neighbors to estimate duration, therefore, for those who have not yet visited the wildebeest exhibit. A nearest neighbor to a returning visitor is a wildebeest viewer who rates other exhibits similarly to someone who hasn't yet seen the wildebeest. So remember Paul's method. First we explore. So here's our data. So we've got visitors and the minutes they spend viewing the wildebeest. We record all these durations. So we'll have 200 wildebeest durations, a mean of 36 minutes, standard deviation of 15 minutes. Here's a histogram. And notice that some people really like the wildebeest and they're a long, long time. And some people just kind of breeze by and then they're gone. Less than 30 minutes at most at the wildebeest. Here's what it looks like as a density plot instead of a histogram. Some spend a lot of time with the wildebeest and some just very little. So the original data includes the wildebeest viewing durations. And we're going to drop that because that's going to be our target. So here's a histogram of ratings. Certainly we would expect 0 because nobody's seen all the exhibits and nobody's rated all the exhibits. So, and then you can see that 1s and 2s, 3s and 4s are the most common, and 5 more than 1 or 2. Notice the mean values are highly skewed to the left. So we can't really use an average here because the average is going to be so heavily influenced by the zeros, which means they haven't rated the exhibit. So how do we choose a similarity kernel? Well, the zeros don't mean a rating of 0, so we shouldn't really use the zeros at all. So if there's a 0, we just used it as an indicator that they didn't see the visit. Okay? They didn't rate the exhibit. So maybe they saw it, but they don't remember it. People often only rate what they do not like. You got to keep that in mind. There's some real bias in this data. And some people only rate the things that they really, really like. Okay? So for our similarity kernel, we want similarity to be based on exhibits rated by both and total ratings by each respectively. So if X and Y are visitor feature vectors, then we don't want to use distances, they use zeros. We don't want to use correlation, the means use zeros. But if the ith exhibit has one or both not rating it, then their product is 0. In other words, we want to use cosine similarity. Notice this sum of products, which we use to define the cosine similarity kernel. Those products are non-zero only if both xi and yi are non-zero. So again, here's the dot product. We've seen that before. Cosine similarity defined in terms of the dot product. And if we had actual data, so this is visitor X and visitor Y, and here's their ratings, then the dot product is only going to include the terms where both visitors have rated that exhibit. So even though X and Y are 150 dimensional vectors, cosine similarity compares them only on a subspace. In fact, in this case, the 3-dimensional subspace. So cosine similarity compares visitors only where such comparisons are meaningful. On exhibits, both visitors have viewed and rated. So let's look at the results. First, we're going to take our data and do a train test split into those who have viewed the wildebeest and those who haven't. And we then do a k-nearest neighbor regressor with cosine similarity, 5 neighbors, fit it to our training data, and then we predict our test data, and then y-test is actual duration values. And then we can compare the two. So notice here are the actuals and y-test. Here's what we predicted using our kNN regressor. Here's a histogram of minutes difference between actual and predicted. So most accurate to just a few minutes. So now we can compare and notice that just visually, these histograms, orange is predictions, blue is tests, and we can see pretty good predictive value there. We can look at correlations, very high correlation between tests and predicted values. And then we can plot y predicted versus y test. And the ideal would be that these two are equal. So the closer we are to this green line, the better off we are. So now we're confident in predicting durations for those who haven't yet seen the wildebeest. So here is our data set of people who haven't yet seen the wildebeest exhibit. There's 50 of them. And now we can predict how long each one of these is going to spend at the wildebeest in minutes based on our nearest neighbor's regressor. So in summary, nearest neighbor methods are great if there's not too much noise, and there's an abundance of data, and there's a natural method for measuring similarity. Even then, however, the similarity metric might be inaccurate, and if we say every time we use exactly k neighbors, then there's some arbitrariness there. So we're going to have better algorithms at some point. But even then, very often it's hard to beat these nearest neighbor algorithms.